All right. All right. So the first thing I wanted to do today was to tell you a couple of things. Let's see. Okay, so I just wanted to tell you that graded assignment, I finished with graded assignment 1. I finished grading that, and then I also graded the special problems. So those are extra credit, so not all of you handed them in, but I did grade the ones that I got. Hold on a minute, something is missing from this. Hold on. Where is it? This thing is starting to confuse me. I probably shouldn't have done this. So confused. All right, that's good. All right, so anyway, so what you should do is look at these, right? Because, you know, some of the problems, well, I mean, problems on the exam could be similar, and, you know, you should look and see what I wrote about those. So make sure you take a look at the corrections that I gave you so that you could benefit from that. And I also want to say that I am grading this GA2 that's due last night. I'm going to do that next. And I also want to say that there are about 10 people that haven't handed that in. And I'm going to give you until tonight to hand it in, which means that tomorrow in the morning, I'm going to post the solutions. And after that, you can't hand it in anymore. And the reason I want to post up those solutions quickly is because this graded assignment 2 is a lot like the last problem on the exam. So I just want you to have the benefit of, you know, seeing what I would think was a good answer if I don't have a chance to grade yours that quickly. But I'm going to try to grade that graded assignment 2, so you'll be able to look at your own answer and see what I thought of it. But, you know, this is about, you know, 50 some in the class, so it will take me a while to get through those. I also wanted to talk about the fact that I had offered some office hours for folks to ask me questions. You know, you can always email me. You don't have to wait for an office hour. You can email me and we can make an appointment. But I want to set up some office hours, say on Friday and maybe over the weekend, just a couple of hours really, so that if you're feeling like you need something explained about a question, or, you know, you want me to go over a problem that's not the one on exam, but, you know, maybe one that's like it or similar to it. So I wanted some feedback on times that would be good for you to set this up. Okay, so I'm sort of going to suggest a couple of things, and I'd like to, you know, see what you think about that. Okay. So, all right. So what about Friday? How's Friday afternoon or even Friday evening? Maybe from 2 to 3 or from say 7 to 8. I just, I wouldn't mind if you could, you know, type in the chat what you think about that, or you can give me a thumbs up if you think it's a good idea, or if you have a better idea, you know, tell me about it. So I need some feedback from people. I got 1 thumbs up. Thank you, Thomas. 2, all right, all right. How about some alternate suggestions for people who are not giving me the thumbs up? So the people, I don't know. So No, nothing. What about on the weekend? Do people want me to meet to have an hour, say on Sunday?
Yes, please.
And Janelle, what time would you like that hour to be?
I don't uh I don't really care. I just work on Friday, so I can't join Friday.
Oh, all right. So how about Sunday, like, how about 11 a.m.? Or no, maybe that's too early for you young people. 1 p.m. I don't know.
Daniel just said 2 to 3.
2 to 3 on Sunday. All right. Well, don't forget this thing is due Monday, so we don't want to leave it to too late. If you'd rather do it Saturday, I could do it Saturday. But any other comments about this? Because I haven't gotten a whole lot of feedback, but I've got a little bit. Okay, that's a resounding, I have no idea. Turn on your mics, people. Give me some feedback. I'm asking for it. So tell me, Friday.
Half of us commented in the chat box. We said 2 to 3 was fine. I don't know if you
I don't
saw it.
see anything in the heck is going on with this chat box. I was just looking at that. Oh, 10 new messages. Duh. Sorry. Someone's asking me about the grades, and there's so little that I have so far this semester that there really isn't. Wait till after this exam, I'll have a much better idea of how you're doing. So yeah, I'm trying to keep the chat box open the entire time. I thought I did. I thought I had it open, but then I saw the little thing that said 10 messages, but where the heck are they? I don't even. Well, I may have two different chats because I have two different things open, and I think I'm confusing myself a lot. So I don't think, oh yeah, here's a whole bunch of chats. Okay. All right. So, so I'm just gonna stick with this, right? Somebody said 2 to 3 Friday was good, right? 2 to 3 is good, 2 to 3. Okay. So 2 to 3 Friday. And I'm actually going to be around, I'm going to do the 7 to 8 also. Does anybody at all think that they would come to that? Otherwise, I'll just get rid of it.
Yeah, I would.
Would do it or get rid of it?
I would do it.
All right, good. That's what I'm going to do. So Friday, 2 to 3, 7 to 8, and Sunday, 2 to 3. That's what I'm going to do. All right. So, okay, good. All right, great. So now I'm going to just move on and do what I was going to do, which is go on with the material. So let me get myself a little more room because I kind of took some of that room. And I have some stuff to go through today. Some of this stuff is really review in terms of the definitions, and, solution. We're moving into the solutions unit. Although there's a lot in common with the previous unit because I still talk a lot about intermolecular forces and things in here. But I want to, so what I want to do is tell you first that I have some things posted on Blackboard, some readings. And there's reading number 1 and number 2. And this one is very relevant to today's class. And also next week's lab. In fact, what I'm saying today is really very relevant to next week's lab. And number 2 is going to be very close to what I'm going to do on Monday. So I know you have an exam, but you have a long time to do that exam, and you don't need that much time to do that exam. So I'm really hoping that you're going to take a look at these readings, because the book, which is OpenStax, right, which is the next chapter that we're doing, it does not cover this material like I do. That is why I wrote these handouts. Okay, these are written by me, and these are really, much more in line with the way I handle solutions. So I hope that you have time to read those. There's also lots of slides today. Some of the things, some of the definitions and stuff, I put them on slides so that I'm not going to be writing forever. And you may want to print some of those slides if you have a printer handy, so that you can take notes on them if you want. I'm also going to do some demo stuff today. Believe it or not, I have some, maybe you could see it over there, some of this, these liquids on my right. Anyway, so what I'm going to do is start with basically some very basic information and some definitions about solutions. And please stop me if you want some clarification or anything like that. Okay, so a solution. A solution is a homogeneous mixture. Homogeneous means, it's uniform. It's the same throughout. A homogeneous mixture of two or more substances consisting of ions or molecules. A solution has what we call a single phase. Okay, what does that mean? A single phase. What that means is if you have a solution in a bottle, you just have one uniform thing. You don't have any boundaries. Okay, this is one phase, or one, we could say one layer. And I'll talk a lot more about this today. This is if you have, say, two layers. This is not a solution. Or if you have a solid sitting on the bottom, okay, then that's a boundary layer here. It's like a boundary between the solid and the liquid, and that is not a solution. So clear is key, really, and when you have a solution. And there's many different, oh, by the way, and of course, with a solution, we say that things are dissolved, okay? So we use the word dissolve to apply to solutions. So if you have a mixture where you have layering going on, or solid sitting on the bottom, then that has not all dissolved. Okay, it's not a solution. Now, many different examples of types of solutions, and the ones that we're most familiar with in this class, well, if we had lab, which we have videos of lab, are dissolving a solid in a liquid, like sodium chloride in water. That's an ionic compound. So ionic compounds dissolve in water. Sugar in water is another example, and that's a molecular compound. So ionic and molecular compounds can dissolve in water, and they could also not dissolve in water, but these are examples of solutions, okay? We also have liquid solutions, like vinegar is actually acetic acid in water, and acetic acid is a liquid and water is of course a liquid. Alcoholic drinks are solutions of ethanol in water, and of course there would be flavor compounds as well. CPDS, that's my compounds definite abbreviation. You can have a gas in a liquid. I actually have an example here of a gas in a liquid. This is seltzer. Okay, you can't, it's clear. You can't tell that there's no layers. If you shake it up, well, then the gas is coming out of solution. But that's a very good example right there. And then there are alloys like 18 karat gold that are like two metals that are dissolved in one another. Okay, so those are some basic definitions, and that's enough to give us a little bit of a start. So when you mix two things together, and mostly in my class, the only things we're really thinking about are solids in liquids or liquids in liquids. Those are the solutions that we make in this class. When you mix two things together and they dissolve, okay, so it looks clear, then that means you have a solution. And I've said that already. I'm saying it many times because it's so important. You have one phase. Okay. You can also for instance, take red food coloring and dissolve it in water. But it's not going to look, it's going to look red and clear. So the key here is that it's clear. It can be colored, but it has to be clear. All right. And so red food coloring would be, would have the color red, colored red, obviously, but it would still be clear. So it's the clarity that really makes you know that something is a solution. And like I said, I'm going to show you some examples, but not just yet. Okay. I just want to go through some other definitions. And here is some things that we already know from last semester. These are terms that I'm sure have been used before in the classes, wherever you took it. The solute. Okay, the solute is the chemical that's dissolved in the other thing. It's the species that's dispersed uniformly throughout the solvent. So the solvent is really, well, that's the minority component. That's the component that's present in the smaller amount. We refer to that as the solute. The other component of a solution, so we say that there are two components of a solution. One is the solute, one is the solvent. That's the majority component, okay? That's present in a greater amount. So we dissolve the solute in the solvent. Other words that we've learned before about this is that we can have solutions that are concentrated, where you have a lot dissolved, or dilute, where you have a small amount dissolved. So we know these words already from last semester, but here's something new. So this is the new thing. We talk about solubility. And solubility of a substance is the amount, like in grams or in moles, of a solute that will dissolve in a given amount of solvent. So one thing that we can express this, like I said, in grams, right? So we can have an amount in grams per 100 milliliters. This is how we often express solubility. Oh, I could dissolve 10 grams in 100 milliliters, or I could dissolve 50 grams in 100 milliliters. I could also express solubility in molarity, which would be moles per liter. That's another way to express it, okay? So there are different ways of expressing solubility. All right. Okay. All right, so this is actually quantitative information. So quantitative information, if you remember, is information that has, involving numbers. So, maybe before I would say, well, that dissolves in that, or that's soluble in that. But now, when we talk about solubility, we're talking about how much actually dissolved. And we've never quantified a thing like that. That's not something that is done in Chem 103. In Chem 103, we have a very sort of general view of solubility. We call things soluble if they have a high solubility. So you've seen the term soluble. Now we have soluble ionic compounds and insoluble ionic compounds. Well, soluble really means they have a high solubility. A lot of it dissolves in 100 milliliters, let's say. And then we also talk about insoluble. Okay, that's really basically in Chem 103, yeah, it's like none dissolves. But that's never true. There's always going to be a little bit. So it's certainly oversimplified in Chem 103. So we're going to take away some of that simplification now. When insoluble really means a little bit dissolves. And the solubility tells you exactly what that little bit is. It tells you maybe 4 grams per 100 milliliters, or maybe 4 milligrams per 100 milliliters. Okay, so there's some very low solubilities that we would call insoluble. Okay, so there's, you know, entire ranges of solubility. And then here's a term you probably haven't heard before: miscible. It sounds like I'm saying mixable, but I'm not pronouncing it right. But that's actually not what this actually has a very specific definition. Miscible means soluble in all proportions. And a good example of this is ethanol and water. Ethanol is the alcohol that's in alcoholic beverages and water. And you can have 99% ethanol and 1% water. You can have anything in between, 90-10, you know, 50-50, 10-90, 1 and 99% ethanol and water. And these are all solutions. So you see what I mean when I say miscible. Miscible means infinitely soluble, soluble in all proportions. And just to sort of drive my point home here about ethanol and water, here's a little chart, and this chart tells you different beverages, okay, different drinks that you can have, and how, you know, absolute alcohol is almost 100%. Grain spirits, 95% ethanol, but then you could have different, like wine, that's 8 or 12% alcohol, and, you know, this beer and stuff like that, and all kinds of other things that have different, even fruit juice has a very tiny percent of alcohol. So you can have, you know, when you buy these things, they're one phase, they're clear. Yeah, you may have some bubbling if you shake it up, if it's a sparkling thing, but generally these are really all solutions. And they're based on ethanol and water, and of course other compounds. Okay, anybody got a question about that? I'm looking at the chat. Okay, and then we have something called immiscible, which means not miscible. Okay, and what this term implies, if you say two things are not miscible, that implies that there's a lack of solubility. They do not mutually dissolve in all proportions. And generally, if you put a significant amount of these two things together that are not miscible, you will see these phase boundaries. And I wanted to talk about the phase boundaries. And that's why I brought these things to show you today. So how am I going to do this? All right. Just do this. All right, so I'm just going to show you some of these things. Move the camera. Can you see that okay?
Yeah.
Yeah.
All right, I can't see it, and so I don't know. Okay, here we go. All right, so what I have here is a few different substances. This is just water, so that's pretty boring. But I wanted to show you butanol and water. Butanol and water is right here. And if you look closely at that, can you see a phase boundary?
Yeah.
Yeah, you should be able to see it like right there, right? There's like a layer on top. And so what this is you've got mostly water in here. Water is on the bottom, and you've got a little bit of butanol on the top. Okay. I have another one. It's butanol in water. This is harder to see, but if you look closely, you could see the boundary on the bottom. Can you see that?
Yeah.
All right. So that is indicative of something, a situation where the liquids are immiscible. Okay, so this is butanol and water. Butanol, by the way, is got 4 carbons. This is 1 butanol. It's got an OH in one place. And I didn't leave room for hydrogens, but these are all hydrogens. Okay, so here's butanol and water in the bottle. And there are 2 layers. So you have the bottom is H2O, the top is butanol. So why would water be on the bottom? Anybody? What's not working here? Double click on her video. Is it working now? Can you see what I'm showing you? I'm just not sure.
I can, but I think a few people can't.
Yeah. I think it's how I'm doing this today, and I don't know how to fix it. It's like
If you stop sharing your OneNote page, then all they'll be able to see is your camera.
but then how do I? All right, so I'll write about this later. I'll just show you right now. Did that do anything? Because I can't see it now. I don't know where it is.
Yeah.
For me, you're my whole entire
You know what?
screen.
I'm getting rid of this. I'm just going to do it the way I always did it. I think that I have, so now I don't know what to do. I'm so confused. Why did I change things today? I was really stupid. Hold on. Very strange. Maybe I have to share the camera. I don't really know. Try that. I can't even see myself on this thing. I don't know what happened today. Maybe I have to leave the meeting and come back. I don't even know.
Well, we can still see you.
You can see this stuff?
Yeah, we can see
Everybody see it?
fine.
All right.
The
Okay.
person who couldn't see you before is because I'm assuming they were on their phone, and on your phone you can't pin stuff, but I'm assuming they switched over, so now they can see you.
All right, okay, then I don't care. I just can't see, I can't see what I'm showing you, so I can't see if it's working, unless I'm the one talking. But it doesn't seem to be going over to me either. Oh, well, I don't care, it's fine. So you saw the butanol. Now I want to show you something that is a solution. So this is just plain old vinegar, okay? And vinegar is actually, I put it in here. Vinegar is already a solution because it's a solution of acetic acid and water, all right? So that's no layering, it's just one solid layer. Well, it's not solid, it's liquid, but it's one layer. So what about if I did this with a solid and liquid? So I'm going to make a solution of, let me put these butanol. Oh, I wanted to show you butanol. Yeah, I forgot the thing I was going to show you, which is, this is what happens when you shake up butanol. Okay, you look at that. Cloudy. Cloudy is evidence when you don't have a solution. When things are cloudy, you let them settle and they layer eventually. Okay, so each of these, if I shake it up, you get extreme cloudiness. That is evidence that these two things are not miscible. So I'll write that all down after, but I just want to show you now. Now, clear, vinegar is clear, right? Shake it up, it's water and acetic acid. It turns clear again almost immediately. And now I have two different solids, okay? This guy, this is calcium carbonate, okay, white solid. And here I'm going to put a very familiar white solid. You can see it's coming out of my salt. So I got these two white solids here sitting on the bottom. And if I put water in them, so this is the calcium carbonate. Shake it up. Cloudy. Here is the sodium chloride. I may have put too much in. No, I don't think so. Shake it up. All right, let's take a look after a little bit. See how that's cleared up nicely, and it will clear up completely. The calcium carbonate certainly will not. So you can see the difference here. You have a solution of sodium chloride and water. All right, it's totally clear, looks just like water. Then you have this calcium carbonate. It just, if you let it sit, it will settle, okay? But, and it will have two phases, because when it settles, you'll be able to see a solid on the bottom separate from the liquid phase on the top. But with sodium chloride, that won't happen because it's completely dissolved. Okay, so what else was I going to show you? The only other thing I was going to show you, a couple of things. I was just going to show you that you could have a solution that's colored. Okay, it just has to be something with a color. So if you put food coloring in water, where'd my water go? There's some water. Everybody knows what's going to happen here. You put a little food coloring in it. I don't have to do anything. It would mix itself. But if you mix it, you see, well, actually I put so much in, you can't even tell it's clear. But it is a solution. There's no separation. And I feel a little silly that I didn't make it a little more dilute so you could see that indeed it is clear. Probably just should have made it in that bottle. See, it's clear. All right, anyway, so it's a bit silly, but you can see the butanol now, the butanol in water, it's starting. I'll show you at the end how it settles out, how it goes back to being those nice layers, but still not dissolved. Now, this is something else I made, all right? So this is sodium chloride in water, all right? But I've added too much and it doesn't all dissolve. So this, I'll talk about in a little bit. I've made a saturated solution. So, all right. That's all I have for that. Let me go back. I think I bit off more than I could chew today. That's all I gotta say. Yeah. Good, nice chemicals. All right. All right. So I'm gonna go ahead and share this screen again. Good. And okay. So let's go over what I did. I had the butanol in water. I shook it up. And you end up with something that looks very cloudy. And then if you let it settle and you wait, what you'll end up with again is your layers, your two separate layers. If you mix acetic acid and water, you will not see any layers. It will just be clear. And this is what vinegar is. Okay, so you shake it up, it's going to be clear. So clear indicates solubility. Layers indicate, or cloudiness, indicate a lack of solubility. Okay, generally, if you have cloudiness when you mix two things together, then it will eventually settle out. Let's see what's happening here. Actually, you could see that the calcium carbonate example, which I think you could see here, you could see it's already settled to the bottom. Okay, so let's go through those two examples. We had calcium carbonate in water. And when you mix it up, so it starts like that. You have the calcium carbonate and the water. If you mix it, you end up with, it's all cloudy. And then if you let it sit, it settles. You end up with, again, your calcium carbonate and your water. Now, this isn't really pure water here, though. This stuff on top here. It's actually a solution of whatever calcium carbonate is able to dissolve in water. Okay, so you do have some calcium carbonate in water. All right. Hold on a sec. All right. Okay, so let's see. So I said that sodium chloride is soluble in water.
Professor, you're not sharing your screen.
Sorry, say again?
You're not sharing your screen.
Oh, right, sorry. Okay. Ugh. Sorry about that. All right, so NaCl is soluble in water, but it's not soluble forever. So how soluble is it? So we want to figure out what is the solubility. What I'm really asking is how much sodium chloride can dissolve in a certain amount of water. And the amount that I like to talk about is 100 milliliters of water. So suppose I have 100 milliliters of H2O, and I add, so here's my 100 milliliters of H2O, a nice Erlenmeyer flask or something. And I add 10 grams of NaCl. I shake it up, and it's clear. So I have a solution. All right, so I add 10 more grams of NaCl, and I shake it up, and it's clear. Still a solution. So can I go on and do this forever? I add 10 more grams of NaCl, and I shake it up. What do you think? Is it going to be clear? It's clear. Okay. Until I add 10 more. And now when I shake it up, there is solid on the bottom. Well, it looks cloudy, but then there's solid on the bottom. And you end up with a situation like this that I made here. And so this is what happens when you add more than 40 grams, more than 36, I should say, grams of NaCl to water. You end up with some on the bottom, okay? So at the end of that, you know, you'll have this, I can't draw, it saved my life, but you will have some solid on the bottom. So basically a lot of sodium chloride dissolves in water. But not forever, right? And for sodium chloride, you can dissolve up to 36 grams of sodium chloride in 100 milliliters of water. 100 milliliters is really not that much. So sodium chloride is really quite soluble in water. But at some point, does anybody know what's that called? The solution becomes what?
Soluble.
Sorry, can you say that again? Saturated. Somebody wrote it. It becomes saturated. So you cannot get any more sodium chloride into that water. Okay, so for NaCl, the saturated solution is 36 grams per 100 milliliters. All right. That's about 6 molar. 6 moles per liter, or 6 molar. So if you have a 5 molar solution of NaCl in water, that's what we call unsaturated, which just means it's not saturated yet. It totally dissolves, okay? So a saturated solution, I have the definition of it down here, is one where the maximum amount of a solute is dissolved. And let me tell you what happens when you dissolve sodium chloride. So what about the process of dissolving NaCl? So you take some NaCl, like I did, you put it in a beaker or something, and at first it's on the bottom, okay? And then what happens is some ions will break off from the solid. So you might have a sodium ion and a chloride ion and another sodium ion, okay? Oh, and what happens is they become attracted to the whatever, you know, if it's sodium, it'll become attracted to the delta negative oxygen end of the water molecule. Okay. If it's chloride, it'll become attracted to the delta positive end of the water molecule. And remember what these attractions are called? What are these interactions here, these dotted lines here? What do we call them? What type of force is that? Anybody? This is what type of thing is a sodium? What is that called? It's not quite any of those. This is an ion, right? And this is a dipole. This is an ion dipole force. Same here. Ion dipole forces. Okay, so we get all these ions floating around in the water that are attracted to the water molecules. But what happens is after a while, after the ions start to build up in the water, what happens is that some of them will start coming together again. And form little clusters. And you will end up with small crystals. So while you have dissolving happening, you also, after a while, have deposition. They call it forming the solid back and back again. So you have the ionic compound dissolving, and then you have the dissolved ions forming the ionic compound again. This first process here is called, of course, dissolving. And this one is called deposition. And so what you eventually have, here's your NaCl solid going to Na plus aqueous and Cl minus. You have dissolving and you have this deposition. And eventually, if you add enough, you get equal rates of these two things happening. And we call that equilibrium. And when this equilibrium happens, this happens after 36 grams of sodium chloride are added to 100 milliliters of water. Okay, so after you've added that 36 grams, that's all that's going to go in. Okay, so if you add more than 36 grams, so supposing you added like 40 grams, you'll end up with, if this is 100 milliliters, you'll have 36 grams dissolved. You'll have 4 grams sitting here on the bottom, and you'll have equal rates of going into solution and coming out of solution, so that this solution here, this stuff above the solid on the bottom, this is a saturated solution of NaCl in water. And this is a double arrow. That double arrow indicates equilibrium, which is something we will see a lot more of later on in the semester. So what's going on here? So you have the sodium ions and the chloride ions. And when you have the solid, you have an array of these positive and negatively charged ions in all directions, and every sodium is attached to a chloride many times over. Okay, and all of these things here, what do we call these lines here? These are a certain kind of bond. What kinds of bonds are these? They're between sodium and chloride ions. Are they covalent bonds? Ionic. They are ionic bonds. So when you dissolve sodium chloride, you have to actually break ionic bonds. Well, that requires a lot of energy, because those bonds are very stable. But what happens is that's not all that's going on. Remember, we talked about how those ions come off and then they attract to water molecules. Those are ion dipole forces. So we really kind of have two things going on. We have the breaking of ionic bonds that requires energy, but we also have the ions interacting with water through ion dipole forces. And even though ion dipole forces are weaker than ionic bonds, there is so many of them. When you have one sodium ion, it probably has, I don't know, 20 water molecules around it. So you have considerable ion dipole forces. So this interaction with water through these ion dipole forces, these are attractions. And they stabilize, they lower the energy, so releases energy. So you've got two things. You've got something that requires energy and something that releases energy. So energy plays a big role in solubility. And I'm going to be talking more about this for ionic compounds. We'll talk about this on Monday. Okay, today I'm going to focus for the rest of the time on what happens when you dissolve molecular compounds. So when you have molecular compounds, you don't have any bonds that are broken, because what's holding those particles together is intermolecular forces in a molecular compound. So what you have in a molecular compound is you have a solute, that's a molecular compound, and the molecules interact by these intermolecular forces for molecular compounds, and you have a solvent. Okay, what if the solvent is water? Well, water interacts with other waters by intermolecular forces. So the molecules interact by intermolecular forces. So when you have separated solute and solvent, they each have their own intermolecular forces. When you put them together, solute and solvent, now the molecules of the solute and the solvent interact by their intermolecular forces, which could be different from the ones between solute and solvent and solvent. So now we have solute and solvent molecules interact by intermolecular forces. So to make a solution, you have to break up the intermolecular forces between solute molecules. You've got to break up intermolecular forces between solvent molecules. And both of those things cost energy, right? It costs energy. But what happens when you put solute and solvent together? So when you put these together and they interact by intermolecular forces, they're attracted to one another. All molecules are attracted to one another. These attractions release energy. So again, you have energy being required to pull molecules apart from one another, solute and solvent, and then coming together, you get some energy release. So it's really all about energy. And so these energy considerations that determine whether molecular compounds will be soluble in each other. Are very important. Okay. And I'm going to tell you more about this, but what I just want to mention before I do that is just another definition, just another type of solution. So I want to just get through these definitions. I talked about how an unsaturated solution is one that you haven't added all that you can add. So for example, for NaCl, you can add 36 grams per 100 milliliters. So if you had 28 grams in 100 milliliters, that would be an unsaturated solution, less than the equilibrium amount. And then you can also have very interesting situation of what we call a super saturated solution. And I'll probably show you a demo of this next week. But so that's where you have actually more solute that's dissolved than you're supposed to be able to have. And this is how you somehow can trick a solution to dissolve more than it really should. And I'll show you that example of that. That's usually happens when you heat up a liquid, a solvent, and you're able to dissolve more solute. And then if you cool it very close, you cool it right, it's mind games with the molecules. So you could heat water, add a solid solute to make a saturated solution. And then when you cool it slowly, it's like you trick the solution. It's like, oh, it's like when the Wile E. Coyote is going off the cliff and his legs are going, and he doesn't fall until he realizes that he's doesn't have ground underneath him anymore. It's like the solution the stuff doesn't crash out, solid drop out of solution until it realizes that it's really got too much dissolved. It's not quite like that because of course chemicals don't have brains, but it is a very non-equilibrium situation and it's very unstable. And if you add a single crystal of the solute, it just crashes out. So I'll show you this next time, I think, or I'll show it to you sometime soon. But what I want to do now is move on to talk in more detail about molecular compounds. Okay, I'd like to talk about molecular compounds either dissolving or not dissolving in each other, either forming a solution. So dissolving means forming a solution, or not dissolving. In other words, not forming a solution or not being soluble in each other. Okay, so maybe you've heard this expression. I would like to know, have you heard the expression, like dissolves like? Has anybody ever heard of that expression? Anybody? A no is a response. You could simply type a no or say a no. You have heard of it, some people? Yeah, no, yes, okay. No, no. There's one yes, two yeses. Okay, good. All right, well, that's what I'm going to try to explain to you is what does this like dissolve like basically means that similar compounds will dissolve other similar compounds. Polar will dissolve in polar, nonpolar will dissolve in nonpolar, that sort of thing. But the question, so polar dissolves polar, most of the time. Non-polar dissolves non-polar. But why? Why is this happening? How can we understand this sort of generalization? Okay, how can we determine when two substances will dissolve in each other? And so I talked about the fact that there's energy considerations involved, right? Right. What your comments are all true. The liquids nonpolar, yes. The reason why bacterial cells don't split open until you put soap in them. That's slightly different. That's not really quite the same, but it's all about dissolving. So how do we determine this? And I said that there's energy considerations, which I'm going to talk about in more detail. But that's not the only thing. There are actually two factors. And one I call the entropy factor. And the other one is the energy factor that I have started to talk about already. Okay, so I talked about this a little bit already. But the entropy factor I have not talked about. And so I'd like to do that first, this entropy factor. So when you think of entropy, you think of usually, well, we haven't learned about it. We're going to learn about it at the end of the semester, very end. But it has to do with the fact that things naturally get messed up. Things get mixed up and messed up. All right. So I guess I would say that there is a natural tendency for things to be mixed. So there would be a natural tendency for things to dissolve in each other. And I'm going to give you some examples. There's some really simple examples. So if you have a skunk that's outside your door, okay, that doesn't smell very pretty, right? The smell does not stay with the skunk. Eventually your house will smell like skunk, okay? So the odor molecules, they spread around, okay? If you took a drop of food coloring, like a drop of red food coloring, and put it in water, but not like I did before, you don't mix it, just leave it there. Leave it. Don't mix it. When you come back, it's going to be spread all around that beaker. Doesn't matter that you didn't mix it. So when you come back, you're going to have an even spreading. It spreads around. Okay. This type of thing also happens with heat. All right. So if you have a room and you have a heater on one side, right? So here's your two walls. And talk about bad artists, but here's a radiator. So it's very hot here. And eventually that heat is going to spread all over the room. Okay, so if you just let nature take its course, nature spreads around substances and energy, right, in the form of heat, which is not what we're really focused on here, but it does do that. And we'll talk about that later in the semester. So if you just leave that skunk odor, you leave that drop of food coloring in that water, you don't have to shake it up. It spreads by itself. And this thing, the thing that increases when energy and stuff gets spread around, we call that entropy, okay? So I tend to call this the fact that nature spreads around substances and energy. I call this the entropy factor. Entropy, you know, we think about it as being disorder, and that's really a good way of thinking about it. Disorder increases naturally. Things spread around naturally. So there's a tendency for things to mix. So that's one factor that's very important. So the entropy factor always favors a solution forming. Because what is making a solution but mixing? Okay. There are some exceptions, but I don't want to talk about them. If entropy were the only factor, then everything would dissolve in everything else. Well, it's not the only factor, right? If entropy were the only factor, everything would dissolve in everything else. But it's not, right? Because I said there's also an energy factor. So the second thing is the energy factor, which I've sort of started to talk about earlier. Okay, so systems tend to want to minimize their energy. So how do we figure out what this energy factor is, and what do we kind of mean by it? So if you have two compounds, two molecular compounds, and you want to talk about mixing them, let's say, you know, you have an energy diagram, and this is the energy of the separated compounds. So what I'm asking is, you know, what is the energy of the solution relative to the energy of the separated? Is it over here? Is the solution over here? Is it over about the same? Is it lower in energy? If it requires a lot of energy to go from separated to forming a solution, right? That we'd say that this is a high energy cost. This would be basically no energy cost. I say this is a high energy cost because this is uphill. It's considerably uphill. Sorry. So if this is uphill, oh, it didn't work. Damn. I'm not having a good day today, really. Thanks for the chat. Ah, good. So if there's a high energy,
Everything.
sorry, somebody say something? No, it doesn't work again. Ah!
They're like, if someone needs it, they go. Mhm. Yeah. No, over there, they have to get up, punch you, kick you. They have to do everything before the doctors are like, okay, just a little bit. And we'll
Right.
see how he does. I'm like, this man's he needs more.
Okay, so, where am I? Yeah, I'm having a little trouble here today. It's not really working for me. I keep getting out and getting back in, which usually takes care of it, but it's not really doing it today. Bringing the big guns here. Ugh. Come on. That's really hard to believe. What is going on? This is so bizarre. Ugh. I don't get it. Am I in this meeting or not?
I can see you.
Yeah, but the thing is, I share my, I have to be in the meeting twice because I use my tablet to write on, and that's why you always see two of me at the meeting. So I can't seem to get in. I don't understand what's going on. I'll just have to work with it. It's really strange. Oh, all right. I don't know. And it's still not writing. So go figure. I don't know. Ugh. Try again. All right, well, oh, there it goes. I don't know. Okay, well, back to square one. I'm sharing my screen. I see it is there. Okay, so if the separated is much lower energy than the solution, then forming a solution has a high energy cost, and it will be an uphill process. If the opposite is true, if forming a solution has actually releases energy, and it's downhill, this is pretty rare, then it's going to form a solution because there's no energy cost, and the natural tendency to mix will make the solution form. Okay, and then what also can happen actually is that there is very little energy cost, or it's about the same. If the energy of the solution is about the same, so energy is about the same, then that also will form a solution because the natural tendency to mix will take over. Okay, so what I'm going to do is go through and tell you, first of all, how do we know what this energy cost is? How do we know what the sign of this delta H, okay, we call it the energy change or the enthalpy change. So the we call it delta H solution. This is the energy change that we're talking about in going from separated solute and solvent to forming a solution. But delta H solution is broken down. We kind of break it down into 3 steps. We talk about taking solute molecules and pulling them apart from each other, interfering with those intermolecular forces, right? And that requires energy because those forces attract molecules to one another. And there's an energy cost associated with separating the solute molecules. So that's the first step. Step 1 is separating solute molecules from each other. This requires energy. And that's because of the attractions, because of those intermolecular forces of attraction between solute molecules. And I call this the energy change for this step, or the enthalpy change, delta H solute. Okay, the second thing, and this doesn't really happen in this order, it really happens all at once. But the second thing is doing the same thing, separating solvent molecules. For the same reason, this also requires energy to break up those intermolecular forces. Okay, we call this delta H solvent. So those two, these are both positive. These both require energy. Okay. But now what happens when we take and put the solute and the solvent molecules together? Okay, they will attract each other. Sodium, metal, and water, it actually doesn't dissolve. I mean, it reacts. It's not just dissolving. Remember how dissolving is? Somebody asked me on the chat, would a negative delta H be like sodium, metal, and water? Sodium, metal reacts with water. What I'm talking about now is not reaction. I'm talking about dissolving. Dissolving is really a physical process. You don't really change the identity of any of the chemicals. So while energy is released when you put sodium in water, it's just not through a dissolving process. So I guess I'd say it's the same in some ways, but different in more ways. So getting back to this, when you put the solute and the solvent molecules together, they interact via intermolecular forces. They attract. All molecules attract, okay? And so this releases energy. I call this delta H mixing, and this is always negative. So the delta H solution, which is simply the overall energy change for going from separated solute and solvent to having them dissolve in each other. The delta H solution is the sum of all these things. Okay. These are positive and this is negative. And so what I'm going to try to teach you is how to figure out, you know, if this delta H solution, does it end up being positive? Is it large? Is it positive but small? Is it approximately zero? Are the energies of the separated solute and solvent about the same as the solution? Or is it negative? And if we know what it is, if we know this, we can predict if two substances will be soluble in each other. Okay. So I have a little illustration of this whole idea of, oh, I think it's on the next page, of this whole idea of putting these together. Hold on a minute. Oh, I've never had that happen before. There's a lot of firsts today, none of which I like. I can't get to the other OneNote page. Boy, this is great today. Oh my goodness. I don't get it. My computer must be too hot. Wow. And now it wants me to send an error message. I don't want to send an error message. Just let me do what I want to do. And now I'm not sharing anymore. I realize that. Okay, so here's my cute diagram. Okay. So what this is simply showing here, so here I have These purple guys are the solute molecules. Separating them, making room in between them, means you have to overcome intermolecular forces between the solute molecules. And then these blue molecules are the solvent. And in order to squeeze the solutes in between them to dissolve, you have to pull those apart from each other as well. Okay, so that's also endothermic, and you'd be breaking up intermolecular forces between those molecules. And then also, finally, when you put the solute together with the solvent, they intermingle. Now you have attractions between the purple and the blue molecules, or are they green? I'm not sure. And that releases energy because there will be some forces of attraction between them. And so we have two steps here that are endothermic and one that is exothermic. And the sign of the delta H solution can be positive or negative, or in many cases, close to zero. So, what's going to happen in the different cases? Okay, how is that going to affect whether the thing is soluble or not? And I guess I would summarize it this way. If the delta H solution is not too high, okay, so if it's not too large and positive, then the entropy factor overcomes it. Then the natural tendency to mix can overcome it. And you will get a solution. However, if the delta H solution is large and positive, then the entropy factor cannot overcome that. And it will not form a solution. And then if delta H solution is near zero, in other words, you have about the same energy for the separated as you have for the solution. So the delta H is zero. Okay, well, then energy is not really playing a role. And entropy is going to rule the day. Okay, then entropy wins. Okay, and they mix, and solution happens. And what do you think is going to happen if delta H solution is less than zero? If it's negative, if you actually release heat when you put the solute and solvent together, well, then the lowest energy is going to win and the entropy is going to win, right? Both energy and entropy would favor a solution forming, and so it would. It's a lot to swallow, I know. Energy considerations make our lives a little complicated. But what I want to do is two very, very sort of practical, two very concrete examples. Okay. And I hope that these will help you understand what types of things, what types of compounds dissolve in what other types of compounds. Okay. So what we're going to do is look at the very first activity. So the two examples, the first one is to consider pentane and water. So pentane being the solute and water being the solvent. Okay. And the second example is going to be methanol and water. And so what activities 1 and 2 do, they sort of go through trying to figure out what is the sign and what is the magnitude of these different delta H contributions, so that we can determine, using that, that sort of theoretical basis, which of these will form a solution and which will not. So I just want to point out that this is the beginning of the activity sheets for chapter 11. And I tell you that you should reading materials are provided. Remember, I mentioned there were 2 sets of reading materials. And so, okay, let's just talk about pentane and water. Okay, so this is pentane over here. You've got 5 carbon atoms and a whole bunches of hydrogens. Okay, so if we look at this sheet, it says, here's the structure of pentane. What forces, what type of forces, what are they called, must be overcome between pentane molecules in order for it to make room, right? In order for it to dissolve in water, in order for it to make room for water molecules. So if you're going to be talking about separating pentane molecules from each other, so I'm asking you, what type of intermolecular force is there between pentane molecules? That's this question. So what's the answer to that question? Do they have hydrogen bonds between them?
No.
No.
That's right, no. What about dipole forces?
No.
No. So what do they have?
Dispersion.
That's right. There's only dispersion forces. And that's because they're nonpolar. Okay, so dispersion forces are a relatively small magnitude. They're not that strong, right? So delta H solute, the energy required to pull apart pentane molecules, do you think it's going to be large or small? Which would that be? If it's dispersion, those forces are relatively, are they strong or weak? They're relatively what? Compared to hydrogen bonding? Weak, yes. So it delta H, the magnitude, delta H solute is small in magnitude. And now, of course, we're pulling apart pentane molecules. So that is going to require energy. It always requires energy to pull these molecules apart, but it doesn't require that much because there's only dispersion forces between them. So if we shift gears now and start to talk about the solvent, right? This was the solute. Now we have water molecules as a solute. So my question is, what forces must be overcome between water molecules so that they can make room for pentane? What are those intermolecular forces called between water molecules? Hydrogen bonds, that's right. And hydrogen bonds are the strongest intermolecular force that we know. Okay. So it's going to require energy. This is going to be positive. It always requires energy to pull these molecules apart. And in the case of separating water molecules, this is going to be large, a large energy expenditure. We have to spend a lot of energy to pull water molecules apart, because of the hydrogen bonds that attract them. So you have to break up all those hydrogen bonds. So now we're into the step where we're talking about the solute interacting with the solvent. So we've got pentane and water, okay? So what forces exist between pentane and water if pentane were to dissolve in water? So you have pentane, which has no dipole, and water, which has a dipole. But if there's no dipole in pentane, it doesn't really help. You can't have dipole-dipole forces. You won't have hydrogen bonding. So what is the only type of intermolecular force between pentane and water? What will it be? Yes, dispersion forces, exactly. And dispersion forces are pretty weak. Okay, so you only have dispersion forces, so those forces are relatively small in magnitude. Dispersion forces relatively weak. Okay. And the delta H, right, when you put those together though, the solvent and solute, it will release energy because these molecules are attracted to each other. That will release energy. So it'll be negative, but not much, right? Because dispersion forces are pretty weak. So basically what's happening here is you're taking, let me see if I can make a little space here. You took your pentane molecules and you separated them. And delta H solute was small and positive. Then you have water molecules and you separated them. And the delta H solvent was large and positive, okay? And then when you bring them together, and you get some interaction between pentane and water, but pentane water interactions are very weak because they're only dispersion forces. So only a small amount of energy is released. So you spent all this energy and you got very little back. So that's a large expenditure of energy. That means that the total, this delta H solution, you have to add it up. You have something large and positive. Oh, sorry. You had for delta H solute was small and positive. And then you had delta H solvent, which was large and positive. And then you have delta H mixing, which is small and negative. So this thing is going to win. You're going to end up with a delta H solution that's pretty large and positive. It's going to be dominated by this. So when it comes to answering this next question, it says, I think overall that delta H solution would be, well, because of the contributions that I have discussed, delta H solution will be positive, and its magnitude will be pretty large because it's dominated by the fact that you had to break up those hydrogen bonds in water. Oh, somebody asked, why was it negatively charged for the mixing? I think you just mean, why is delta H negative for mixing? Delta H is negative for mixing because whenever you have an attraction, that releases energy. And you always have attractions between any molecules. They're just not that strong, okay? Because they're between pentane and water, they're only dispersion forces. So you always have an energy released when you bring two molecules together, and you always require energy to pull them apart because there are always attraction between molecules. So basically we have a situation where we have the separated solvent and solute has to go uphill to get to the solution. And so this delta H solution is large and positive. In conclusion, these substances would not be able to dissolve. The answer is would not. Why? Because you needs too much energy input. If it was a little bit of energy, then the entropy factor could overcome that. But this needs a lot of energy. So the energy of the solution here, see how I've drawn this higher up than the separated. The energy of the solution is higher. Oh, that's nice. Just bought me right out of OneNote. Energy of the solution is higher than the energy of the separated solvent. And whenever this is higher, that goes against, right? Because the energy cost is too high. So it goes against forming a solution. Now, the natural tendency to mix always favors forming a solution. But in this case, if I ask like which wins, which, you know, here we have such a large energy expenditure that I would have to say energy wins. And you can't form a solution when you have that much of a delta H to overcome, okay? Too high a delta H solution to overcome it, for entropy to overcome. And so you do not get a solution forms. So no solution. They don't dissolve in each other. Okay. So that's the situation with pentane and water. I guess we'll start next time with methanol and water. Okay, and I think I have those office hours, 2 to 3, 7 to 8 on Friday, and Sunday 2 to 3. Hope that was it. Okay, all right, everybody. If you have any questions, you can stay. Otherwise, I'll see you on Monday or maybe at my office hours.
Thank you.
Oh, you're welcome. That was a bit crazy today, but made it. You too.
Have a good one. Bye.
Yeah, bye.
Hey, Professor.
Yeah.
So the graded assignment 2, I submitted it through email because on the Blackboard, I don't know, it didn't let me. Is that okay?
I did save that. Yeah, I got it.
Okay, thank you.
But you didn't do the explanation, which is a big part of it.
Oh, I said I did it